We're going to do a variety of different formulas that are going to be given to you. So earthquake intensity, sound is another one, pH of acids and bases, this butterfly question. They're all applications of logs. So the scenario might be different, they might be the same. What you have to be able to do is to be able to convert some exponential equation to a logarithmic or logarithmic to exponent and actually solve for it. So we're given this formula, okay? And there's a couple things. We get dB, which is the loud sound, dBO, which is the quiet, 10, which is just a number, and then we get this intensity ratio. So this might just be however many times louder something is. Louder something is, okay? All right, so let's use this formula in this scenario. So we have a sound of 80 decibels, so that's that first part. 45 times louder, that's the intensity, so that's 45 over 1, okay? And we don't know what the softer sound is. So we're going to go dB minus dBO is equal to 10 log I divided by IO. So 80 minus dBO is equal to 10 log 45. And you can actually calculate what 10 log 45 is. Okay, so what we're going to do is we're going to rearrange, and if you rearrange, you're going to get dBO is equal to 80 minus 10 log 45. And you can actually calculate that. You get, did I skip a question here? Losing it. I skipped a question. Totally skipped a question. Well, we'll come back to that one. Okay. 80 minus 10 log 45, if you calculate that on your calculator, you actually get 63.47 decibels. So therefore, the softer sound is 63.47 decibels. All right, well, how about we go back to the earthquake question, the one I skipped. All right, so the Richter scale talks about things exponentially, and we're going to use this formula at the top there. So starting off, I over IO is equal to 10 to the exponent m minus MO. All right, so we have the weaker magnitude, which is the MO, and we have the stronger magnitude, which is the M. So we can create this equation where I over IO is equal to 10 to the exponent 4.1 minus 3.4. So I over IO is equal to 10 to the 0.7. And if you calculate that, you actually get 5.01. But to the nearest whole number is going to be 5. A weak earthquake has a magnitude of 6.5, so that's our MO. And the following day, a strong earthquake occurs with double the intensity. So our intensity is 2. So what is the magnitude of the stronger earthquake? So in this case, we get 2 is equal to 10 to the m minus 6.5. Now, converting this to log form, we're going to get log base 10 of 2 is equal to m minus 6.5. And if you rearrange, you get log plus 6.5. So log 10 of 2 plus 6.5. And again, you can calculate that on your calculator, and you will get 6.80. M equals. So therefore, the stronger earthquake has a magnitude of 6.80. Okay, a strong earthquake with a magnitude of 6.7, so that's our MO. Sorry, our M. And our MO, we don't know. And our intensity, so our I over IO, is equal to 3. So we get 3 is equal to 10 to the 6.7 minus MO. Changing that to log form, we get log base 10 of 3 is equal to 6.7 minus MO. Rearranging, we're going to get MO is equal to 6.7 minus log 10 of 3. And finally, calculating that, you get 6.22. So therefore, the weaker earthquake is 6.22. All right, well, we already did this one because I can't turn pages correctly. So one sound has a loudness of 78 decibels and the other has a loudness of 100 decibels. So we start with the louder sound minus the quieter sound is equal to 10 log of the intensity ratio. Okay, so 22 is equal to 10 log I over IO. And just cleaning up this a little bit, we can divide each side by 10. So we get 2.2 is equal to log I over IO. And changing this to exponential form, you can actually get base 10 of 2.2 is equal to the I over IO. And once more, I over IO in this case is going to be 158.5. So therefore, this sound is 158.5 times as loud. Okay, pH questions. So we're given this equation here. All right. A beaker of acid has a hydrogen concentration of 3.5 times 10 to the 6 moles per liter. Calculate the pH. So pH is equal to negative log 3.5 times 10 to the negative 6. So let's calculate that one. And we will get negative log 3.5 times 10 to the negative 6. And close off our brackets, hit enter, and you get 5.46 if we round that correctly. So the pH of this acid is 5.46. If a beaker of acid has a pH of 4.1, calculate the hydrogen concentration. So in this case, we know the pH is 4.1. We don't know the hydrogen concentration. So let's change this to exponential. So the first thing I'm going to do is divide by negative 1 to get rid of that negative sign. And we end up with negative 4.1 is equal to log H positive. Now the base of this log is 10. It doesn't say it, but it is 10. It's the default. So we get 10. The hydrogen concentration is 10 to the negative 4.1. And if you actually calculate that, you're going to get 7.94 times 10 to the negative 5 moles per liter. Don't forget our units. Okay. A beaker contains a solution with a pH of 4.9 and the other one has a pH of 7.6. Determine how much times higher the hydrogen concentration is in the stronger solution as compared to the weaker one. So the battery's low and the iPad's low. We'll see if we can make it here. So step 1 is calculate the concentration of the first, a pH of 4.9. So in this case, we're going to get 4.9 is equal to negative log H positive. Rearranging this, we get 10 to the negative 4.9. If you're wondering how to do that, look at the previous one. Okay, now step 2 is calculate the concentration of the one that has the pH of 7.6. So in this case, we get 7.6 is equal to negative log H positive. So H positive is equal to 10 to the negative 7.6. Now to finally calculate how much times higher it is, you take the 10 to the negative 4.9 and divide that by 10 to the negative 7.6, and you actually end up with 501, which means the stronger solution is 501 times more hydrogen concentration. All right, 2 more questions. There's a logarithmic relationship between the butterflies and flowers. In one study, scientists found that the relationship between the number F of flower species that a butterfly feeds on and the number B of butterflies observed can be modeled using this function. So predict the number of butterfly observations in a region with 25 flower species. So that is our F value. So we can put that in for F. All right, now we got to do some rearranging. So start off by adding 2.641 to either side, and you will get 27.641 is equal to 8.958 log of B. Clean it up a little bit more, dividing each side by 8.958. And you will get log B is equal to 3.0856. And B is equal to 10 to the 3.0856, just changing that to exponential. So B is equal to 1,217.92, which we will round to 1218 species. So therefore, I predict there will be butterflies. Observations, anyway. Okay. And the last one's dealing with welders. So welders wear helmets fitted with a filter shade to protect their eyes from the intense light. So we get 2 variables here. We get the filter shade number, and we also get the fraction of visible light. So then we're given the shade number. So that means that's going in for n. So let's substitute. And then we have to do a little bit of algebra. So subtract 1 from either side. Multiply each side by 3. And then you're going to divide by 7. We're running out of room here. All right, so far we've got 33 over 7 is equal to negative log of t. All right, changing this to exponential form, we get t is equal to 10 to the negative 33 over 7. So t ends up being 10 to the negative 33 over 7. (1.9 times 10 to the negative 5, 1.93. Okay. And there's your answer. That's the fraction of visible light.